Hello. My name is Philippe Biondi. I think I am mostly known for being the creator of Scapy. But today I'm not going to talk about something I did, but things I've seen that I think are interesting in the domain of software bugs. So title is failure is not an option, with a little star at the end. We'll see why later. First, this is the ancestor of all bugs. You may already know it. So it was a moth inside a relay of a big old computer. It's the ancestor, and you thought the bugs I'm going to speak about, I mean, this kind of bugs do not exist anymore, but actually they do. So here you have ants, spiders, or cockroaches. So that still exists nowadays. Did I say I was speaking about software bugs? Oh, yeah, I did. So it's okay. I'm going more to speak about bugs like this one. This is the Steam installer that could clean your home. The guy that did it found it scary, but still he did it. And the result was some unhappy people. I'm going to go through many bugs. They are public, so you may know already some of them. I hope I will show you some that you don't know and that are, I think, interesting. This one, so I'm going to show you different kind of bugs first. This one was interesting. It was in an office. And the office door are keycard protected, so you had to swipe your badge to enter. But the door was slow to open. So you have to wait 5 seconds, maybe 30 seconds, sometimes even more, before you can enter the room. So everyone has his ninja technique to open them. So some said you have to swipe it very slowly. Others say, no, you have to swipe it very quickly. Some others say, no, you swipe once and then you wait. Others say, no, you have to. And some tried standing on one foot or whatever. The result was always the same, you had to wait. So one day, an employee stayed late and alone in the office and he heard clicks of doors being unlocked. So he just asked what was happening. Eventually, he found the authentication server. And it turned out that the log file was very big. So each time the program was trying to open it, to open a line and to close it, it took a long time. And actually, all the card swipes were queued correctly. And the software was still working on the card swipe from the day before. So the problem was made even worse by people swiping a lot of time their card. And actually, the door was not 30 seconds long to open, but 30 hours. So if you understood correctly, 30 seconds was the time you had to wait maximum before any door would open, thanks to the swipe of a guy the day before. So long for the physical security. So he removed the log file and then everything worked as it should. So this is another shape of bugs. Bad guys too have bugs, so it's very trendy nowadays to do ransomwares. So in this case, the guy derives the AES key. So everybody knows what a ransomware is. Yeah, I guess so. So he derives the AES key and IV from libc. So it's not a very good idea for the entropy. And he seeded it with the current timestamp. So it's even worse. And it means that you can recover the key from the file creation time, and you don't need to pay the ransom. So this is nice for when you are a victim. There is another one. The author wanted to simplify his task of managing many keys, so he decided everybody will have the same AES key for all these files. So the ransomware encrypted the file and did not store the key, because it was the same everywhere. The author of the ransomware kept the key he used everywhere, and that was it. Except that a programming error made the key actually random. So no way to recover the file. Too bad. Another one, this one I like it a lot, so maybe I have already presented it to some of you. It's RC4 implementation error. So here RC4, you have a state that you initialize, and you scrabble it with the key, and the scrabble is done by exchanging values in the array, for instance, in index E and G, and then you generate the key stream by exchanging also values between the array E and G, index E and G. So can you spot the error? Well, it's very difficult. So I show you a good implementation. Did you see? Okay, so this is what changed. This is on the variable swap. So this is a classical way to make a variable swap. But when you are an experimented programmer, what's the point of being experimented if you do it the way you learn it in school? So you have to show off. You will use those kind of stuff to exchange variables, and you can say, yeah, and I even did not use a temporary variable. I'm optimizing the memory consumption, etc. So here, this is what what works. It actually works. And this is what does not work. So I'm going to make a demo to show you the effect. Okay, so here I have a working RC4 implementation that will encrypt Cuckoo, and you see it's encrypted. You can decrypt it too. And you can see that my RC4 bad is also interoperable with the working version. And you see also it's encrypting correctly. And now I'm going to look at what a random an encrypted stream looks like. So I'm going to echo a lot of capital A and encrypt them with the good RC4 program. So you see something encrypted, okay? Now I'm going to do the same thing with, do you see it, RC4 bad? And not to go sufficiently slowly, I'm going to use less as pager. So you see, RC4 bad also encrypt. But if we wait a bit, don't you have a strange impression? No? Is it coming? So at some point, the plain text begin to appear. So it's very interesting to have something that seems to work, that works on small test vectors, and when you don't even need any cryptographic attack to recover the plain text. So what did happen? When you do this, this is supposed to be the working idiom, and this is supposed to be the same thing. It should work. But actually, it's not the same thing. Here you have variables, here you have an array with indexes. So when we have this special case, this translates to this. Okay? So it's like we did this. So actually, instead of exchanging two values, we set it to a value with itself, we set it to 0. And the RC4 state Philippe's with 0, one index after the other. So you end up with an RC4 state fill of 0, and the output is taken from this state. So it quickly degrades to a sequence of zeros, and you XOR your plain text with zeros. So you see what you have what you've seen previously. Okay, so I like it very much. Okay, another one, another kind of bug is what we call the double-checked locking pattern. So here we have a classical way of doing singletons in Java. You have a helper class that you want to be a singleton, and you create a method named getHelper that will either instantiate the singleton if it is not yet instantiated, or that will return you the already instantiated class, so that there is only one instantiation. So obviously there is a race condition here between the test and the creation, So here it will be working only on a single-threaded version. To make a multi-threaded version, you add this keyword so that this will be atomic. Okay, it will work. But it will be less, because of this, you lose some performance. So there is a pattern named the double-checked locking pattern that will help you be quicker for most of the cases where you don't need to instantiate the singleton, which is this one. We do a test without synchronization, and if it's good, then we return it. It's the most of the case, but if it is not, then we synchronize this, we test again, and we instantiate it. So this is supposed to work. It has even been a design pattern, so something you can trust. But actually, this is what would happen, for instance, after a just-in-time compilation. You will create space here for your object. You will put this points to the field helper. And this is actually the constructor that is instantiated. So you see that your field helper will be non-null before the initialization of the class. So here, the test that is not synchronized could test this and be without synchronization, and could think the helper class is already instantiated, while it is not. So you still have a race condition here. So this is another bug, which is not directly visible inside the code, but depends what will be done after. Another one is the compiler optimizations. So here we have a check for integer overflow. But the compiler may decide that this means that length is negative, which cannot happen. So the check can be removed. And then you think you made the check, but you are still vulnerable to an integer overflow vulnerability because of the compiler. And you could have written it like this, not so as not to trigger any overflow. Okay. So this was about the shapes, the shape of bugs, different shapes that it can take. So now I'm going to speak about the impact. So this is a router I bought 3 years ago. The first thing I did was to go to the network analysis tab and try a good old shell injection. And it worked. Woo! So I was there. I'm the king of the world. I just rooted my router. Then one tab not so far away, I could configure SSH, put my key, and I was root too. So actually, I already was root. So here I escalated privilege to where I already was. So it was useless. Well, it's a bug. It deserves to be fixed, but I did not gain anything. On the contrary, this is a textbook case of buffer overflows. It's an old CVE on whois. So you see the patch, sprintf becomes snprintf on the argument. So it's straightforward. So it's whois is a non-privileged program, not SUID. It means that actually if you use it, if you exploit it, you escalate your privilege to where you already are. And then you think again, and what about all the websites proposing a whois service that actually is a CGI calling whois? Here you escalate your privilege from anonymous web client to a local shell. So here it seems there was no impact, but there was. Another case that was where it was very hard to analyze the impact was Shellshocked. So if you remember the bug, you had a bash that allows attacker to execute commands through specially crafted environment variables. The impact obviously was a web server using CGI script that called bash. But you also had OpenSSH that was impacted because if you were a restricted user, you could bypass the force command with the SSH original command. There was also an impact on some DHCP clients because some of them call bash scripts and transmit the DHCP server parameter through environment variables, and probably many others. So it was very hard to analyze the impact. But there is another one that is even more difficult. It was the Debian Openssl crypto disaster. So in this case, the entropy for key generation was limited to 15 bits, which means that obviously there was an impact on SSL TLS and all the X509 certificates, but also on SSH host and user keys that were generated while Openssl was vulnerable, but also Tor relays, for instance, but also Diffie-Hellman session keys could be recovered. So perfect forward secrecy was broken. So there is an impact in the past. That was hard. And it's not finished. You could have strong DSA keys, and the fact of using them while your random number generator was flawed will leak them. So actually, the impact is contagious. The strong DSA key could be leaked and become, you will have to revoke also strong keys because you have used them only once with a bad RNG. And probably a lot more. Okay. Okay, so here I have a small part on what we can do to avoid or to find bugs. So we have best practices like software configuration management, version control, bug tracker, coding style. So you all know about this. We use software engineering to make sure we create correct programs, that interfaces are great, API work. We have a software architect. We can work with requirements, V-cycle or agile method. We have procedure. We can be ISO 2001 or something. We have assurance levels like MISRA software guidelines. So this is more specific for embedded. We have ISO 26262, the DO178B on for avionic embedded systems, etc. We have also formal methods like model checking, abstract interpretation, theorem provers. We do test campaign, automatic, manual, fuzzing, a lot of things. We have certifications like common criteria or the DO178C, etc. We have a lot of things, but bugs still happen. For instance, the USS Yorktown was a ship. In 1996, it was used as a smart ship program testbed. It's like a smartphone, but with a ship. And so they put 27 Pentium inside it, and it becomes smart. 1997, a crew member entered a 0 in the database field. Division by 0. Crash all computers, propulsion system fails, and the ship is dead in the water for 3 hours. Yes, only for a 0. Not very smart. F-22 Raptor, first flight from Hawaii to Japan, all system crashed when crossing latitude 180. You know, it's an international date line. So you go from 180 to minus 180. And everything crashed, no more navigation. So they had to follow their tankers to go back home. This one is quite well known, Mars Climate Orbiter. One team used English units. The other metrics unit. There is no need to say more. So it crashed. This one is about Patchwork Missile. The time was tracked by 0.1 increments, but there is no exact representation in binary floating point. It means that the time tracking slowly drift, and in 100 hours, the drift was 1/3 of a second, which is equal to 600 meters at a missile speed. And it means he could not follow his targets. And it happened that he missed one Scud missile that make 30 dead people because of this. The workaround until it was fixed was to reboot the system regularly. There is a similar one for the 787. So there was a communication saying that if he is up for 248 hours, which is not a normal operation situation, but still, you can lose all alternating current electrical power due to generator control units simultaneously going into failsafe mode. And 248 days, it's 2 at the power 31 hundredth of second. So is it a coincidence? This one is less fun. It's the Therac 25. It's a radiotherapy machine used in the 80s. It was a VT100 terminal connected to PTP11. It's quite old technology. And you had two modes. Direct low energy beam or Xray mode using a high energy electron beam hitting a target that will create X-ray. And this is what could happen. And it's not good. So it was a very big engineering failure. First, you had no hardware interlocks to prevent high energy mode with the target. Previous models had it, but this time they said software is sufficient to be sure that this never happened. It was coded in an open loop controller mode. That is to say, nothing was here to check the hardware is operating as the software thinks it is operating. There was some error, like a flag that was set by incrementing and decrementing it. And it means that sometimes you set it, but it overflows, so actually you just resetted it. So it's bad. And one of the difficulties was to reproduce the case where there was a problem. And it was when hitting X to select X-ray, then you say, oh no, I wanted electron. So arrow up, E, okay, electron, enter, and B to beam on. If you do this in less than 8 seconds, 8 seconds is the time for the target to go under the beam, then you will actually be in without the target and with the high energy mode selected. And it did not happen in tests, but when the operators get more used to the machine, they were quicker and quicker to operate it, and this began to happen. And this step displayed a malfunction 54, which was not documented. So the operator pressed P to proceed anyway. And also, when they saw that something strange happened, the vendor always denied that overdose could be possible because of the so many safe logs they made in the software. So it also took a lot of time because accidents happened in at least 3 places. They could not help each other to prevent it because of information sharing was not sufficient. And this one also is a big failure, is a Toyota unintended acceleration. So it's a very nice euphemism because I think it was like 90 dead and several injured. So you had a lot of problems in the process in the processor running the car. Some critical variables were not protected from corruption. That is, say, for instance, storing them in different parts of the memory twice or 3 times. No hardware protection against bit flips, and they said they had, and they did not. You had the bug bingo, buffer overflow, invalid pointer dereference or arithmetic, race conditions, unsafe casting, stack overflow. The cyclomatic complexity, which is a measure of complexity of a function using the control flow graph of the function, was rated at over 50. 50 is the limit for, we say that over 50 it's not testable because you have too many branches, too many cases to test. So you have 67 function over 50, and the one that is used for the throttle angle function, which is the one in cause of all those accidents, was over 100. They used recursion. Recursion, so it's very dangerous when you have a fixed size fixed size stack, which is a very this is what you have a lot in embedded system and real-time systems. And they also failed the worst case stack depth analysis. So you had stack overflows. They made a watchdog that monitored only one task out of the 24 running, and this one was useless. So any one of those one could die. It did not reboot anything. And there are a lot more. So if you want to spend some time, you can read those slides. Very interesting. Okay, so why do bugs still happen? Best practices are not followed. I think in the case of Toyota, they did not even have a version control or bug tracking. Tools are not used. Formal methods did not prevent them because, well, that was a bit unfair from my part because actually they were invented after most of the cases I presented. And they have been developed precisely to happen this from happening again. But in the case of Toyota, for instance, they already existed, but they were not used because of time money constraint or also because of incompetence. They cannot be applied yet to most of our non-critical complicated software like OpenSSL or JavaScript code. And they only find what they've been made to look for. For instance, if you use a static analyzer made to prove that code do not have any runtime execution error, it will not find a drift in the case of the Patchwork Missile. And reciprocally, if you use a code that is able to analyze the error margin on floating points, it will not find an invalid pointer dereference, for instance. Complexity, systems are more and more complex, but we are not smarter than we were 100 years ago. Maybe we have more experience, but we have the same brain. There is a human condition, so we are tired, the mood change, we can have hangover. The way we work, we have a working memory that is very volatile. It lasts at most 20 seconds. You know, when we try to do an addition or multiplication in the head, you see that you have to repeat what is in your head, not to forget it. Or when you take a phone number, we give you a phone number, it's very hard to keep it in mind. And this is your working memory. And we use it, for instance, when we program. We, for instance, create a variable and you say, oh, I need to remember to declare it. So remembering to declare it takes one place in your working memory. And your working memory can only hold, we say, 7 plus or minus 2 things. A thing can be a number or a digit. This is quite funny, for instance, that you can remember a phone number if you have 5 numbers, like we do in France, but you can't if I give you 10 digits, because 10 is too much, but 5 is okay. To give you an idea, this woman, she has a plate and a drink. And let's say she has 2 working things, which we call arms. She can't eat, because there is a high cognitive log. She can't eat anymore, because there is no more hand free. Here, you have a low cognitive load, so you can eat and drink. And here too, you have a low cognitive load, so you can eat and drink more. You have communication issue like same units, ambiguous APIs, etc. Problem of natural selection versus marketing. So this was a very old cartoon I liked, so I put it here. It was about why Windows was winning against OS2, and nobody understood why, because one was like water in the desert, and nobody bought it, while people bought sand in the desert. So it's true that marketing is not helping natural selection. End users, so there are a lot of things to say about end users. So they make mistakes, they are unpredictable, and They will click on links. They will open attachments. They will plug USB thumb drives they find in the parking lot. They will. So how do we do? We need to live with bugs. So first, keep it simple. Don't do complicated things. Try to do small things and to do them correctly. Hardening, compartmentalization, so least privilege separation, using SE Linux, AppArmor, packs, jar security, sandboxes. There was a very, very interesting keynote done at KernSec that was making a parallel between security and car safety. The name of the conference was Giant Bags of Mostly Water, which is what we all are here. So some of you is mostly beer, I think. So in the 60s, the whistleblower was telling that vehicle interiors are so poorly constructed from safety standpoint that it is surprising that anyone escapes from an automobile accident with serious injury. There was also a book from a journalist named Unsafe at Any Speed. And the engineer said, we don't understand. The cars are safe. They do not explode when you run them correctly. They do not catch fire. The fumes do not go into the vehicle. They go outside. Accidents are due to bad drivers, so education will solve the problem. Cars are made to go on roads, not to have accidents. So does it sound familiar to you? But if we look at nowadays cars, the mindset has changed. So you have 3-point seat belts, pretensioners, airbags everywhere, ABS, electronic stability control, head injury protection, life modules, collision sensor, independent mandatory crash tests and public rating, and a lot more. Well, there is Toyota, but still things have evolved in the good direction on those points. And now a car is designed firstly to protect the driver and its occupants if there is a crash. You can look at this video about an old car against a new car. And it speaks by itself. Other thing is shame. So shame, it was some time ago, having lice was synonym of poverty and bad hygiene. Lice, c'est les poux pour les Français. Hein? Lice, c'est comme souris, mouse, mice, louse, lice. Repeat after me. So having lice was synonym of poverty and bad hygiene, which is not the case, but it was what people thought. It was a mindset. So they were ashamed to have them. So they did not tell anyone. They treat it, they go home, they treat it, and then they come back and no, nothing, it's okay. And other children could be infested without noticing. For example, if they have only the eggs, and then 10 days later, infestation come back, and then the new ones, they don't tell anybody, and it carry on, and everybody had them, but nobody told because of shame. No mindset have changed. When a child has some, all the classroom is informed, and everybody will treat them and will look for them so that they are erased in one time. Does it sound familiar to you too? This is exactly what happened when somebody get an APT. A long time ago, nobody tells, but all the companies got them without telling the neighbor. And actually, you clean it, but the other one get it, and then they come back again and again. And nowadays, things are beginning to change slowly. This one is also very interesting. It's a programming contest where the goal was to optimize non-player characters in a game. So here you have an example of the behavior of a non-playing character. So it was a parrot, and you have all the things he could say to react to the player actions. So the file is very, very, very long. You had a lot of actions, and it was also very, very, very not optimized. So you think you have a lot of things in common. And the game was to optimize it in size and also in execution time, because if you have a lot of decision to take before finding the new action, it takes more time than if you have a very well balanced decision tree. So you must create a program that optimizes it. Your program must run in less than 30 minutes, and you have 72 hours to write it. So complex problem, limited time, there will be bugs. Okay? So now, if we look at the winner's solution, they remarked that the input is a valid output. Okay? It's not very well optimized, but it's valid. It's a working definition for a non-player character. And it's semantically the same as the input one, because it's the same. And they said it's better to give a non-optimized valid answer than a wrong answer or no answer at all. And they also remarked that it's easy to compare an answer with the input by evaluating it on several points. If they do not match, you know there is a mistake. If they do match, you know that it's probable they are equivalent. But maybe not, but it's still probable. So what they did, they used a supervisor. The supervisor initialized a variable with the input, and it runs several optimizers. Each time an answer is proposed, it is tested against the input. If it is correct and better than the current answer, it replaces it. And at 29 minutes and 30 seconds, it outputs the current best answer, whatever is still running. With this strategy, they could code optimizers that were not right always, optimizers that could have bugs, that could crash. The complete program will always be giving an answer that is valid. And I think it's a very good strategy to make sure that your programs go and do their goal. You also have the story of the chaos monkey. So in the cloud, resilient architecture should handle the crash of machines. And the chaos monkey is a program made by Netflix that runs in Amazon Web Services, and its job is to randomly terminate instances during working hour, so that they always put their resilience procedures to the fire. And this is what they said: the best defense against a major unexpected failure is to fail often. So they always live with instances that are terminated, and they should be recreated. There should be failover, and because it can happen, if something goes wrong, at least it's during working hours. You don't get paged in the middle of the night because something crashed. Okay, conclusion. Defense in depth, everything can fail. Make things that can work in degraded mode. Use supervisors, watchdogs, and think one move ahead. And to conclude, failure is not an option, and the definition of option for me was something that you can avoid. So, in fact, failure is not something that you can avoid. Thank you.
Okay, Philippe terminated somewhat earlier than preview. So, we have a lot of time for questions, I guess. So, anyone wondering what will be the future of bugs with all these chase?
Hi. Hello, hello. Okay, thanks for the talk. What kind of techniques do you use at here at Airbus? Do you use all the techniques you presented here, or just some of them? Are they all practical in the real life?
It depends on what software we are speaking of. We always use bug trackers. We always use version control. For instance, where I work, we have a quality procedure that I happen to be responsible of. And because where I work is a lab, we try to adapt the procedures to the day life of people and how they work. And this procedure is completely different from the one you have in the teams that work on for instance, on the autopilot of a plane. So here we don't use V-cycle or agile method or anything. The procedure is very simple. It just says you have to use a bug tracker, you have to use version control, you have to make backups, and you have to document a bit what you do. And so it's a simple procedure and it's very efficient for when you work in labs and you only make prototypes. But when you go to safety critical software, we use static analysis. We use very complicated and very strict requirements. We have to go through certifications like the DO 178, which is very, very strict. For instance, in planes you will find things developed twice with different architectures, etc. Which means that we try to be as safe as possible. And well, I think what is important, for instance, if you apply the same thing in when you do safety critical programs and when you do prototypes, it's quite bad because then people will not apply it. So it's important to adapt the procedure to the place and to the goal of the software you develop.
Okay, thanks.
Firstly, thank you for a very interesting talk. You mentioned some industries in which there used to be a lot of bugs and not much care, which then changed their practices. From looking at this, do you have ideas about how this change of mind can happen? I'm particularly interested in the current state of the Internet of Things, where the state of security is extremely poor. What can we do to change that so that some of the techniques that you're talking about may be more widely used?
I think it's quite sad, but the only incentive you will have you will find for people to fix their bug and to work more cleanly is money. That's why whenever they could go fast to market, whenever they could spend less money on developers, they will do it. And if they understand that it's better to work cleanly instead of fixing after, then this will be one step forward. But I think that you see, for the Grehack 25, for instance, it was the 80s. I mean, the program was made in assembler on PDB 11. It was another world. And we did not speak about software engineering. We did not speak about bug trackers, agile things yet. But now we do. And still you find Toyota, for instance, that make safety critical code and that do not even follow the first beginning best practices. So I'm pretty sure it will happen in the Internet of Things too, because you will have, you don't need to be a big company to make that. You can be two in a garage and you can make a thing in the Internet of Things. You will need to go faster than the competition, and there will be a lot of bugs. That's pretty sure. And also, it's not that safety critical, except maybe for logs, and even that you find a lot of things a bit strange. So I'm pretty sure that sadly it will still carry on to happen, and the only incentive will be money.
Just a remark. At some point, you said that there was a shift in the car making world, where today making a car that doesn't protect people inside is a bad reputation, gives a bad reputation. Maybe in the future, producing bad code, well, it has started to happen, but still it's in the early stage. But producing bad code at some point may give a very bad reputation, and so maybe that's a way also to avoid this. Well, okay, so last chance for a question, and if there is no question, we will go directly to the next speaker. So thank you again, Philippe.